Yeah, thank you very much. It's a great pleasure for me to be here and to be invited to this wonderful and exciting conference. So my talk is about black holes as open quantum systems. Now, in ordinary quantum theory, we understand the quantum to classical transition in the following way, that we consider realistic situations where you have to take into account an environment. An environment means additional degrees of freedom, which are irrelevant, and the interaction with the environment creates entanglement, and the quantum systems, if they are strongly entangled, they become classical appearance. Now, black holes are also quantum systems, and we are here to discuss black holes as quantum systems, and I want to discuss here aspects they are similar to open systems quantum mechanics. So I do not talk here about a particular recent paper. I just assemble some papers that I and others have written over the years, and to discuss this aspect. Now, as we all know, and I don't have to go into the details here, Hawking in 1975 has calculated that the black hole is not really black, but radiates with a temperature proportional to h bar, the Hawking temperature. And this is the usual picture, and you all know how he did calculate it at that time, with following these rays back here from Scri plus to Scri minus, using Bogoliubov coefficients, and then calculating the expectation value of the number operator, which is bilinear in Gaussian annihilation operators. Yeah, so this the famous Hawking temperature, going with 1 over the mass, and the numerical value is very tiny. This is why we face this empirical problem of testing it. The 3 Kelvin microwave background radiation is much hotter for ordinary astrophysical black holes than the Hawking radiation. And so this is the expectation value of nk, which has this Planck distribution. And from this Planck distribution, the conclusion is drawn that the radiation is thermal with a certain temperature. Now, because of that, because of the temperature, black holes have a finite lifetime, and here I've given this lifetime following this old calculation by Don Page of the 1970s, and using just the emission of gravitons and photons dominating this, you get this numerical factor, but important is that the lifetime is proportional to the initial mass cubed, and I've inserted here the Planck unit. So you see this very huge time of 10 to the 67 years for astrophysical black holes that we also had yesterday. Now this approximation that Hawking and others use is an approximation that does not use quantum gravity, but only quantum theory on a curved background. So it breaks down if the black hole approaches the Planck mass mp, because then we assume, at least heuristically, that full quantum gravity effects come into play. Now, the information loss problem, I would really like to rephrase it in the way that where you talk about quantum states and quantum systems, because it's always a bit tricky talking about information. So the issue is whether in a closed system, a pure quantum state can go into a mixture, or whether for the closed system the trace rho squared is preserved or not. Because if you think that the black hole shrinks and it left only thermal radiation behind, then of course you would have for the full system a transition of any state, pure or mixed, into a thermal state. And you know that in ordinary quantum theory, for a closed system, we have a conserved entropy, which is this Gibbs or von Neumann entropy, trace rho logarithm rho, also meaning that the evolution is unitary. And this is the issue, is the evolution unitary or not? So Hawking in 1976, he assumed that the information is indeed lost, and he introduced this description by these superscattering or dollar matrices, where the density matrix evolves into another density matrix that cannot be written as a scattering operator rho times scattering operator dagger. Well, I remember this GR meeting in Dublin when he came to a different conclusion from the ADS-CFT conjecture. But this is still, I mean, one of the options. The other option is that the full evolution is unitary, but this cannot be seen in the approximation used here in the semi-classical approximation. Or the third option, there's a remnant somehow having all this information about the initial state. Now, I want to emphasize, this was emphasized before here, that the final answer to this can only come when we have a theory of quantum gravity that we agree on and that is empirically tested, because the issue is about a full evolution, not about only the macroscopic black hole when we start with. I mean, if you have the evaporation, what happens at the end? I mean, there seems to be a singularity inside, at least classically, and of course if the things are swallowed by the singularity, then information is lost trivially. But we all think that in quantum gravity the singularity is smeared out and there's something else. So the issue is about, I mean, you have the initial state and then asymptotically you have a final state, and is the entropy, the Gibbs entropy preserved or not? Is unitarity preserved or not? I shall focus here on the second option. So I assume, as we assume in ordinary quantum theory, that a full evolution is unitary, and with respect to the time that we have at asymptotic infinity. So I do not assume that we have this information loss and that there is a remnant. And I want to study some consequences of this assumption, whether we can understand within the unitary evolution the issue of the information problem and the thermal nature of Hawking radiation. Now I want to emphasize some points. First, at no point in his original calculation, and also in calculations by others, is an exact mixed state or a canonical ensemble used in the formalism. I mean, there are only pure states are used, but then there is the calculation of expectation values. Now, the expectation values of the particle number operator nk, which is a dagger A, and this has a thermal spectrum, but there's no exact canonical density matrix used here. And in fact, already in 1975, Leonard Parker, who is also here at this conference, he showed that the coherent superposition that Hawking had used is just indistinguishable from a local density matrix, and I will try to make this more precise by own calculations later. Now, in quantum optics, you have, of course, the coherent states, but you have also very prominent states called squeezed states. Now, they are states where, of course, they have to obey the uncertainty relation, but you can have one of the delta x and delta p become very small at the expense of having the conjugate one very large. For example, you can squeeze a state in the position and have it very broad in momentum, or opposite way. And there's a general result that if you have a so-called two-mode squeezed state, so two modes means here, I mean mode with wavelengths or wave number k and one with minus k. So if you have a two-mode squeezed state and you trace out one of those two modes, that is, you calculate a density matrix for one mode only, then you get a thermal state, a canonical ensemble. So this is a theorem you can find in quantum optics textbooks, and it's used in quantum optics. And it also holds here. So in the Hawking radiation can be described in quantum optical terms, and Krishuk and Sidorov have done this in 1990, and what results is a two-mode squeezed state. So if you have, say, the picture that one of the modes is somehow inaccessible, for example, behind the horizon, you trace it out, you automatically get a mixed state outside. But there's something special here. In the case of the black hole, this temperature does not depend on the wave number k. You get just the Hawking temperature. In other situations, for example, in the context of inflationary universe, discussing primordial fluctuations, you can also do these things, but there you have a temperature that would depend on k. I shall also consider also a hypersurface in the black hole spacetime that fully stays outside the horizon and where we can evolve, if you want, in Schwarzschild time, which is outside the quantum states, non-perturbatively, and see how it mimics a local mixture. So this refers to calculations I did with Jean-Guy Demers, almost 20 years ago. At that time, we based it on the, not on the Schwarzschild black hole, but on the then popular CGHS models, which are the two-dimensional black holes with a dilaton. But you can translate these results into the Schwarzschild. So here's again the picture from before, and so we considered hypersurfaces, not depicted here, but that are locked here at the bifurcation point, but then we evolve, in a sense, from early times to late times. We have a massless scalar field, phi, on the background of a collapsing star. Well, in our calculations, we use this solution that was found in the context of the CGHS model, which is this shock wave that produces the dilatonic black hole. So this is what was used in the calculation. And you get, if you start from an initial vacuum state, if you like the Bunch-Davis vacuum, the Gaussian ground state of this massless scalar field, then you can solve the functional Schrödinger equation for each mode, and you arrive at this state psi, which is a product of all these psi k's, and the psi k is written down here. So it's a pure state, and you see it says here the hyperbolic cotangents. It's important to have here this IKT, and this is the scalar field in Fourier space, phi of k. Now this is a pure state, but if you calculate the expectation value of the particle number operator, which is A dagger A, then you get the thermal distribution, the Planck distribution. But you could see the difference to a Planck distribution by just calculating higher order correlation functions. If you calculated not expectation value of A dagger A, but say A dagger A, then you would get a result that is different from a thermal ensemble, right? So this is in the Schrödinger representation what you call a two-mode squeezed state, which you can generate from the vacuum by having these operators e to the ak, a minus k. So this is a pure state, and as long as we have hypersurfaces outside, so it's pure. Of course, we could also have hypersurfaces penetrating, and then you could trace out part of the interior, but this is not relevant for the argument. Relevant is that you can only work with pure states. So in a sense, you have in these pure states an entanglement between the k and the minus k, between the particles, which is not a classical correlation. In quantum optics, you can rewrite those states in terms of squeezed states in terms of two parameters called the squeezing parameter r and the squeezing angle phi. So what are these? If you, for example, depict in phase space p over x the uncertainties, or more precisely contours of the Wigner function, then you get an ellipse. So the coherent state would be a circle centered at the origin, the squeezed the coherent state, and the squeezing then makes an ellipse. And depending on the direction, you have an angle phi, and depending on the axis of this ellipse, you have the squeezing parameter r. And the standard way of writing this is in this form. So this pure state here, which is written down here, can be written in this form with rk and phi k. And you see it's a Gaussian, everything is Gaussian, and you have a frequency which, or here, a parameter in the exponent which has a real part and an imaginary part. So the squeezing parameter can be given in the following form. So it's given by the hyperbolic tangents of r is e to the minus 4 pi omega gm. And the squeezing angle, very simple, just minus kt, so just have a linear rotation in the angle. So you see that if for very large wavelengths, so in the ultraviolet, k to infinity, this r goes to 0. So there is no squeezing. And if you go to infrared limit, which is k to 0, rk would go to infinity. If you just inserted here the maximum of the Planck spectrum for the Hawking temperature to get an idea of a number, then this r is very small and 0.25. This is a squeezing that quantum opticians in the laboratory can generate easily. If kt is 0, we have a squeezing in phi, and if it's pi over 2, we have a squeezing in the momentum. And if you calculate the ratio of the corresponding widths, then it's just given by this number, which at the maximum of the Planck spectrum is 0.37. So very normal numbers. This brings me to the following, to decoherence, because in quantum optics we know that squeeze states are very sensitive to decoherence. Now, decoherence is the irreversible emergence of classical properties by the interaction with irrelevant degrees of freedom. And so coherent states have been found in the sense of decoherence to be the most classical ones. They're really not sensitive to any perturbations by the environment. And squeeze states, especially if you have squeeze states that are squeezed in momentum and very broad in position, they're very sensitive to interactions. Usually interactions with the environment are in position space. So if you have a state very broad in position, then of course this state is very sensitive. In a sense, you measure the particle and localize it in this way. So just let me say a few words about decoherence without going into many details, but I also apply it then to the black hole case, so I should spend some words. Now, decoherence, if you have a quantum system coupled to an apparatus, then as von Neumann already discussed in 1932, there's a problem, the measurement problem, because a superposition from the system would somehow be transferred to a superposition of the apparatus states. This seems to become even worse if you couple many degrees of freedom of the environment. But the point is that those degrees of freedom of the environment, they escape irreversibly. For example, if you have a problem for a dust particle that you put into a superposition, and then if you let it interact with, say, photons scattering off, then the photons disappear. Unless you have them in a small box and you make an experiment like Arroche and his group did in Paris, then the photons disappear. So the photons are no longer accessible, and the environment is not under control. So if you have a superposition, n corresponds to the system and phi n to the apparatus, and initially you have a switched off state for the environment, then this interaction, this scattering, leads to this huge entangled state here. But all the observations that you can do here, they do not involve the environment, so you have to calculate the reduced density matrix by tracing out the En. And if you assume, as is realistic, that different environmental states are approximately orthogonal, because otherwise they would not locally scattering, then you get this reduced density matrix, which looks like an approximate classical stochastic ensemble. So you see, if you only were given this density matrix without knowing about all this interaction, then you would conclude, well, we have a classical apparatus state and we just have a probability of this to be to the right, say, or to the left. So it was formulated as follows: the interferences exist, well, in the full state, but they are not there in a system. Okay, there are many examples, and in quantum optics, you create Schrödinger cats in cavities, and okay, these are not animals, but they are superposition of Gaussians, of coherent states, and the density matrix of this would just correspond to these 4 peaks, the diagonal ones, which are the probability of being here or here, but here you also have off-diagonal ones because you can bring this to interferences and to transition rates, so this is a non-classical state. But if you include an environment in a standard way that I don't discuss here, then you see the probabilities remain, but the off-diagonal peaks, they go down. This means that you have an approximate transition from an and, the state this and this, to an or, which is the classical, that the system is there or there. You can also calculate the Wigner function. Now, the Wigner function is a quasi distribution in phase space, and it can become negative, indicating the non-classical feature of the quantum state. So the Wigner function, which is this transform of the density matrix, Here, for this state here, if you have no environment, just the two Gaussians, then you see here those two peaks, and you have here in between these wiggles, which are give you the information about the interferences. And again, if you then do introduce the environment, you calculate the full evolution and you trace out the environment, then you see how the wiggles begin to disappear. Now it's interesting that in this case, this is not my topic, but I mentioned it, I discussed this with Lajos Diósi 15 years ago, that at least for the simplest master equation, there's a finite time when the Wigner function becomes positive. Yeah? In the density matrix, the off-diagonal terms, they are always there, only asymptotically zero. But here you can make an estimate for a time when all these negative peaks come up to the positive. I want to emphasize that this has been experimentally tested by many experiments by now, starting 96 with Arroch's experiments and also Vineland's experiments, the US, and both these experiments were mentioned in the Nobel Prize for Vineland and Arroch as an important contribution, among others. And these are nice experiments that are done in Vienna, or have been done in Vienna, reviewed here in this paper, where you have big molecules, fullerenes and beyond, that you can put through a double slit, and you have interference patterns. But then you introduce, in a controlled way, the environment. For example, you introduce some gas that flows into the cavity and scatters with the fullerenes, or you can heat up the fullerenes, which means escaping photons. And here on the left, you see the visibility of the interference pattern over the pressure. Here, when in the first case, when you introduce the background gas, and this is here not a fit; it's the decoherence calculation. What Jos and C did in '85, actually, for such cases, and you see that this agrees with the experiment. Here you have this heating case that you have the escaping photons. Also, there you see that the visibility goes down. Okay. So squeeze states are very sensitive to decoherence. This we know from quantum optics, and this is tested in the laboratory. And this sensitivity, for example, is responsible for the quantum to classical transition in the early universe. I mean, according to our standard scenario, which is the inflationary scenario, at least that most people subscribe to, all the structure in the universe can be traced back to quantum fluctuations at the onset of inflation, starting from the Bunch-Davies vacuum. And then when you have stretched the modes beyond the Hubble radius, then in a quantum optic language, they become squeeze states. And these squeeze states, actually, they turn out to be very broad in position. Position means field amplitude. And therefore, if you have even very small interactions local in field space, which is the usual case, then they become decoherent and become classical. And this is what you see in the CMB. In fact, the Wigner ellipse becomes frozen in that case. And so this can also be studied for the black hole. Yeah? So you can study it for the early universe, which would be a different issue, but you can study it for the black hole. You can see, starting from this pure state that I heard earlier, which is just a massless scalar field in a collapsing background, you can do this. You can calculate the sensitivity of the state to decoherence. This is what is summarized here on this slide. So what it turns out now for the black hole case, for our model, that the Wigner ellipse rotates with a certain time scale. You have this squeezing, and you have the ellipse, and it rotates, and the time scale is given by 14 GM. I always have only spherical symmetric Schwarzschild black hole here. And this is, of course, much smaller than typical observation times that you have, and therefore you can do a coarse graining with respect to this squeezing angle. Yeah, I mean, these are fractions of a second for astrophysical objects. So you can have this rotation of the rotation of the Wigner ellipse, but you can smear it out to a circle. Yeah, so this would be the decoherence, and you can calculate then the entropy of this smeared out ellipse, basically the logarithm of the phase space volume, and what you get is in fact a well-known expression that you find in the thermodynamic textbooks. So you have the particle number, nk, and sk is 1 plus nk times the logarithm minus nkl, and nk, which for large squeezing would go to 2r, twice the squeezing parameter. Now, if you integrate over all modes, all wavelengths, then you get this standard result that for the Planck radiation, that the entropy is proportional to the temperature cube, the temperature just being the Hawking temperature. And this is the entropy of Hawking radiation, of course, not the entropy of the black hole. It's the entropy of Hawking radiation. This means that a pure squeeze state is indistinguishable from a canonical ensemble with a Hawking temperature, although the hypersurface we considered stays outside the horizon all the time, and you have a pure state. It's just if you have this squeezing and you have an entanglement, then you get this effective canonical state. Of course, you could say, well, if I go to times, if I could observe Hawking radiation at time smaller than this, which is about 10 to the minus 23 seconds for primordial black hole with this mass, then of course you could see the difference. But there you would really have to find a primordial black hole with that which you could observe on such a short time scale. Yes?
Could you just clarify something? Are you saying that the decoherence time time? Because in normal discussions of decoherence, you have to take into account the nature of the decoherent environment, like its temperature and the interaction strength and so on. But you haven't told us what the rest of the universe consists of here.
This is true. I mean, this is very general. So in concrete decoherence calculations, what you do, you have your system and you model your environment, for example, by a set of oscillators and with a certain interaction. Right. And then you start with a pure, you start with say a product state of system and times one of the environment. You plug this into this full Hamiltonian with the interaction term, and then you calculate, say, the rate of deseparation, and then you typically find very small numbers, like milliseconds in this. This is not done here. I mean, here I use the general argument known from the interaction of squeeze states in quantum optics. So here in that case, there is no particular model with oscillators behind.
But you have to have some external degrees of freedom.
Yes, I have to have. I have to have external degrees of freedom, right?
I mean, there's no lack of them in the universe.
Yeah. So if the black hole were an exactly isolated state with no degrees of freedom, then of course you would have no decoherence.
Right. So,
but as I will show soon, if you're already the Hawking radiation itself, in a sense, can serve as a decoherent environment for the black hole, not for the Hawking radiation, but for the black hole. Yeah. But you're right. I mean, if you need an environment, I would have to maybe go to a string effective action or something with degrees of freedom that are traced out. Actually, there was a calculation in string theory, and I will also mention this.
Right. But the essence of your argument is that you're exporting the problem into the universe as a whole, and then we just need to confront, does the universe evolve according to a unitary?
This is true. This is the idea of having it as an open quantum system, and this openness, right? That you, if you have an exactly closed system, like in quantum mechanics, the decoherence things, if the fullerenes were exactly isolated, there would be no decoherence at all.
Right. Okay. Thanks.
So you could say that although we have this two-mode squeeze state, the thermal nature of Hawking radiation, in a sense, arises from decoherence. Well, these arguments may not apply after the page time, because then the Bekenstein-Hawking entropy equals the semi-classical radiation entropy, and some things in the calculations would change. I have no idea how, but I would, to be on the safe side, not extrapolate this too far. Now what I just mentioned, of course here I talked about a Hawking radiation, but also the black hole is a quantum system, and you could also have the black hole, say, in superpositions, and so say a superposition of a black hole and a white hole So yesterday we have seen concrete examples of such things. And so what happens if when you expose them, these superpositions to environment, would you expect decoherence or not? And in this same old paper with Demers, we have actually studied the decoherence of black holes by its own Hawking radiation. So what did we do? I mean, we started actually from the Wheeler-DeWitt equation of canonical quantum gravity for the black hole. And after semi-classical approximation, you have a semi-classical quantum state of the black hole times this Gaussian state, which describes Hawking radiation. And this is of this form e to the I s naught psi. But you could also have a superposition. You could add, because the Wheeler-DeWitt equation is real, so you could add here the complex conjugate, and you could interpret it, whether it's precisely enough is a matter of discussion. You could interpret it as a superposition of black hole with a white hole, because the complex conjugate somehow the time reverse. Or you could, another example that we did, a superposition of the black hole with no hole, where you just have here the Minkowski vacuum. So there's a black hole state, coming from the Wheeler-DeWitt equation. Of course, there's also a case where you have no state, and you could superpose them. And we have discussed this and traced out the Hawking radiation. That is, we have used the earlier quantum state with the phi field, traced it out, discussing the density matrix, and shown that, in fact, decoherence is efficient, that even if you had such weird superpositions of black hole and white hole, or black hole and no hole, that they would actually resemble an ensemble of having one or the other. Yeah, here this was also actually done for string black holes in the same spirit. So you had in string theory you have these extremal black holes, and you know that in '96 Strominger and Waffer have calculated the entropy for those black holes and finding the standard result. You have here these BPS states where the mass of this generalized black hole is equal to their string charge, and that, you calculate the entropy indirectly, because if you modify the coupling strengths, then you can go from the deep range, from the weak coupling to the strong coupling black holes, and you can calculate the string entropy by string method here, and you see that this coincides with the Bekenstein-Hawking entropy. Now Myers and all independent Amati, what they did is they took somehow the excited string states, the very massive states which are beyond the Planck mass as environment, and that if you trace them out, then you have decoherence and you have information loss, and they conclude that black holes exist only as macro states, just because of that, because a black hole, this was also our interpretation, a black hole is such a classical object, because the event horizon is a classical notion. It's a space-time notion, and if you believe in, say, standard quantum gravity approaches, such as the canonical approach, of course there's no fundamental space-time. You have quantum states on the space of all three geometries. Recall quantum mechanics, there also you have no particle trajectory. The trajectory is something that you have in the classical limit, and the trajectory emerges, if you like, by the interaction with the environment. Heisenberg once said that the trajectories only emerge because of the observation, which you could interpret in this way. And also here, so the black holes come into being in a sense by the decoherence, so they would be totally different quantum objects if you had not the environment. You mean the higher string excitations? Well, they consider it, I could not claim that I have understood all the string calculations, but they have taken those into account. And they have especially Amati has a more technical paper. They have a superposition of, say, the usual state that we have in string theory, where you neglect this higher excitation, and they take into account like you can do in an atom, a superposition of the ground state and excited state. This is what Amati basically did, and then conclude that you trace out these excited states. So there must be there something. Yeah, yes. This is what they assumed, that they are there somehow. So their environment, okay, here were many non-Mendry coupled fields of excited string modes. Now another issue that also refers to the subject of openness is the following. I mean, yes, there are the so-called quasi-normal modes, which are very important in studying black holes, and which maybe so far have not been used in much detail in discussion of the information loss problem. So the quasi-normal modes, so if the black hole, before the black hole settles down to its final stationary state, it emits modes, gravitational modes, that are damped, and like if you hit a bell, and escape to infinity. And they are typical for the black hole. So you have the typical spectrum. John Wheeler and others long ago investigated it. So for the Schwarzschild black hole, if you have a fixed angular momentum of the perturbations, you have a countable infinity of the modes that you can label by the integer n. And they have this spectrum. So this is what was calculated, I mean, quite a while ago. Omega n. You have a real part, which is logarithm 3 over 8 pi gm, and you have an imaginary part, which gives you the damping, because you have e to the minus I omega t, and the imaginary part gives you the damping. And the real part has this universal value, which is called omega q and m. This is a logarithm of 3 over 8 pi gm, which you could also rewrite in terms of the Hawking temperature as logarithm 3 times a Hawking temperature over h bar, numerically given by this result. So this is something classical, okay? It's nothing related to quantum theory, but can you connect it to the quantum properties of the black hole? Yeah, and you can. So the idea is to treat a black hole, well, an oversimplified way, but you can try as a harmonic oscillator with the frequency of these modes. And then also, again, quantum optics, we know that the measurement of an oscillator, or the position of an oscillator, has a fundamental limitation that goes beyond the uncertainty relation, so which is a stronger limitation. This was discussed by Caves in '82, actually very interestingly in the context of gravitational wave detection, because there you have to use a very high sensitivity to have this very small delta x's that you have to measure in the laser interferometers. And in this process, a minimal noise temperature is added to the system. So Caves showed that whenever you have a coupling of such a system with an amplifier, you have to amplify the modes to measure something, you add some noise. And this is a result, I think, well known in that field, delta XQL, which if you had the usual harmonic oscillator, you would just have square root over h bar over m omega as your fundamental delta x, but here you get this logarithm of 3 from this consideration. So it's a bit larger than the uncertainty relation limit. And this is especially relevant for experimental physics. So in solid state physics, you use that when you want to reach the so-called quantum limit. For example, people discuss issues as coupling a nanomechanical oscillator to a single electron transistor. So there are papers in Nature and so on by solid-state physicists using that. And I have, some time ago, then applied this consideration to the black hole case. So I have assumed that these omegas there are the omega of the quasi-normal modes. So if by the coupling of the system to the amplifier, you get, according to Caves and others in quantum optics, a minimal noise temperature automatically just by observing, by measuring those modes. And this is the noise temperature, and it's given by this expression. Now, what is this curl G? The G is the so-called gain of the amplifier. I mean, really the strength how you amplify your signal to really see it. For example, if you have in gravitational wave measurements. Now, if we apply this here, we have to use g to infinity. Why? Because the signal is strongly damped in the limit n to infinity. Now, so if n to, you see, if n going to infinity here, then this becomes dominant, and this gives you the damping. So in order to measure this signal in that limit, you have to have a very large amplification. So g to infinity. So the noise temperature gives you, then follows to be h bar omega qnm over kb times the logarithm of 3, which if you insert your omega here, yeah, is just the Hawking temperature. So the logarithm cancels out. So if you had never known about Hawking temperature before, say history would have been different perhaps, and you would just have asked the question in quantum optics for the classical black hole. You want to measure those quasi-normal modes, and then you add a noise, then you would find that you have here a limitation, and that this noise temperature cannot be smaller than a temperature that is given by Hawking temperature. Now, this may be just some accident. It's certainly also true for higher dimensional Schwarzschild black holes, but for other black holes, for the Reisner-Nordström or Kerr, you do not find this result, but you find some result that is larger than the corresponding Hawking temperature. For example, for Reisner-Nordström, you still find the Schwarzschild black hole as the minimal noise temperature, although for Reisner-Nordström the temperature is smaller. So this is maybe a coincidence, maybe not, but it's another aspect of saying having a black hole not as an isolated thing, but also considering these quasi-normal modes as belonging to the black hole space-time in a very important and fundamental way. I was thinking about also maybe justifying the black hole entropy or the Big-Einstein-Hawking entropy from the quasi-normal modes. They are treated classically, but fundamentally they should be quantum. So you would have a quantum degrees of freedom coupled to the black hole that are not chosen by will, but they are typical for the system. They are a characteristic of the black hole. And maybe you could justify the Big-Einstein-Hawking entropy just as an entanglement entropy with the quasi-normal modes. But I do not know whether this is possible. Certainly I could not see it. I mean, the point is that the spectrum of the modes is universal. It's the only universal thing that we have. And if we want to have this universal entropy, then maybe we could use them, yeah?
Another question, if I may. What happens if you apply your analysis to the de Sitter horizon? Mm-hmm. Do you get the de Sitter temperature, or is it different again?
I have to admit that I did not do the calculation for de Sitter. But this is an interesting suggestion.
Right.
Yeah, I did not do it for de Sitter. I only studied the ordinary black holes.
I think it would be very simple to do that.
Yeah, it would be very simple. Yeah, just did not occur to me to study that. I also looked into this BT set, and there also you get this result. But of course, this is not what you have in mind. So I do not know whether the universality of this entropy has something to do with the universality of the quasi-normal modes, but at least it could be something that deserves further investigation, although calculations are very complicated, and I have not followed this further. Well, the last thing in the last 2 or 3 minutes that I have is also to go to canonical quantum gravity. I mean, what we all would like to see is how the non-perturbative evaporation of the black hole is being described in full, by wave functions. I mean, there are all these limitations, and but one could still ask the question, well, if assume we had the solution, we had a wave function that gives the full non-perturbative evolution, how would we interpret it? What could we conclude from it? And this is what the question we addressed in this paper with Jean Matteau and Paulo Moniz, who is also here at the conference. So we mimicked the black hole and the Hawking radiation by a set of oscillators, introducing various interactions to mimic back reaction, also having the kinetic term of the black hole oscillator as an indefinite kinetic term, as it is the case in the Wheeler-DeWitt equation. Yeah, but without having the usual complicated features of it. So this is a thing that you can calculate in full and exactly, and assume that the real calculation, if we could do it, would also give such states. What could we conclude? Yeah. So this is what I wrote here. So the results are, I don't go into the technicalities, that without a back action, if you just had switch off, that the black hole would become a strongly squeezed state like the Hawking radiation, but the back action would suppress it. And then we calculated the reduced density matrices for black hole and Hawking radiation. And if you have a strong back reaction, then what happens is at the end you have a quantum state, but where you can no longer distinguish between Hawking radiation and black hole. So the difference blur between the two. There's only one strongly entangled state. So what we did is we calculated the density matrix for the black hole. So X refers to black hole degrees of freedom, and so if we calculate just the probabilities, then we produce this graph. So at the beginning you have not yet any interaction between the black hole and the Hawking radiation, and okay, here goes time, and these are just the contours of the quantum state of the density matrix. So here you have a Gaussian state, and this white region is just the strong amplitude that you have here. And if you then, well, here time goes here, but if you increase the back reaction, that what happens is at the end you will have just this density matrix that looks like that and reaches a stationary state, if you like. And if you do the same for the Hawking radiation, so which is the Y, then we also started there with Gaussian states, but if you increase back reaction, maybe it's not so easy to see, but again you get a similar picture for strong back reaction. So if the back reaction is large, the difference between the black hole and the Hawking radiation begins to disappear. You have just one entangled state. Of course, you would then expect decoherence with other degrees of freedom, but as long as you have these two, you see that there is no evaporation in the sense of the explosion of the original paper, black hole explosions, ? But you just have one entangled state of a very non-classical feature. Okay, the summary and outlook. So I would emphasize that black holes, at least in many aspects, should be treated as open systems, because the black hole states, they are certainly correlated with Hawking radiation, but also with other fields in the universe. Certainly, the 3 Kelvin radiation is there and others. So we should take this into account. For example, in quantum mechanics, what USNC in '85 calculated was a dust grain in intergalactic space, and which is certainly something very isolated, it seems, but if you put this into a superposition, the 3 Kelvin microwave background radiation and its interaction is sufficient to decohere it. So black holes also, at least if they are big enough and not microscopic, should also be treated like that and not as a fully isolated quantum system. So they are classical irreversible objects. So like the trajectories emerge as a classical limit in quantum mechanics, so in a sense black holes should emerge as the classical objects from quantum gravity. The information loss problem, in my opinion, can only refer to the total system of black hole plus Hawking radiation plus everything else, even if there are wormholes, maybe to other universes, whatever. And if we have this total quantum state, and we have unitarity for the total quantum state, then of course we can inspect what happens, say, for the Hawking radiation by tracing out irrelevant degrees of freedom. So certainly the observation that we have a density matrix resembling a canonical state does not mean that any information is lost. Right? You would really have to study really the full system of everything. Well, it's as Paul Davies said, in principle the whole universe, but it depends on what you can consider. Black hole plus radiation plus maybe also in astrophysical environment, of course, for other photons and so on that interact.
For these calculations, there's just two things in it, the black hole and radiation.
Yeah, the last calculations. And this earlier general, when I made these general remarks, on the Wigner ellipses. This was Paul Davis's question. There I could assume a general environment.
So when the black hole disappears and I have only radiation, then I'm back to a pure state.
Yes. So the thermal nature of Hawking radiation can be understood to emerge from decoherence, and if it's inefficient, then you could have a superposition of black and white holes, but for at least macroscopic black holes, it seems that this superposition is suppressed, and whether this has relevance for what we discussed yesterday is of course an issue that one would have to study. I also mentioned these quasi-normal modes of the black hole. They, just by having this quantum optical measurement process of omega Q and M, you get a minimal noise temperature, which is the Hawking temperature, in a new way to see the Hawking temperature. Whether the quasi-normal modes play a fundamental role understanding being the origin of the entropy is an open issue. I think it has not been shown that it has something to do with the Q and M, or it has nothing to do. So these were some aspects of black holes as open quantum system. I have not included technical details, and it was also about more an overview about many papers, but I hope I have convinced the point that this should be taken seriously. Thank you very much.